Good afternoon, everybody. Thank you very much for taking the time to participate in today's call. My name is Andy Cross, and I'm AECOM's project manager for this review of next generation carbon capture technologies project that we're undertaking for BEIS along with the University of Sheffield. So welcome everybody. And this workshop is the second stakeholder engagement activity associated with this study, or the second workshop. And the emphasis of this workshop will be on the application of next generation carbon capture technologies across waste, industrial and power generation applications. So we'll move to the next slide, which is the agenda, and I'll just quickly run through what we've got planned for today's call. As this may be the first call associated with the project that some people have attended, the first thing we're going to do is just give a quick recap on the objectives of the study, what it's intending to cover, and then we'll give you an update on the study progress and summarise the objectives for today's workshop. And then following that introduction, we'll get to the main part of the meeting, which will give an introduction to the technologies that we're considering in the study as next generation technologies, and to some of the technology suppliers that are developing them. Some of the technology suppliers have prepared short video presentations of their technology to summarise their features, benefits and applications. And once we've shared those, we'll open the floor to invite feedback and discussion from everyone on the call. There'll be an opportunity to ask questions of some of the technology suppliers that have presented today. I believe most of them should be on the call. And also we hope to gain feedback on the specifics of deployment of carbon capture in various industrial applications. The next part of the workshop will present the preliminary outcomes of one aspect of the study, which considers a concept for a pre-deployment verification demonstration plant. This plant concept is intended to help to de-risk the deployment of carbon capture on industrial sites and support investment decisions for site owners seeking to implement carbon capture. So we'll give a brief summary of the concept and its objectives, and then we're very keen to get feedback on the relevance of that to different applications. And again, there'll be some discussion. That's planned at least to fill most of the 2 hours that we have allocated for the workshop, but we'll hopefully have time for a quick wrap up at the end to summarise things and look at next steps, including how this study fits into call 2 of the CCUS Innovation 2.0 programme and other BEIS and ZIP opportunities. And BEIS will say a little bit about that when we get to that point. I should also just mention, as hopefully you've seen as you've logged into the call, that this meeting is being recorded, and hopefully everyone's okay with that, that there's no issues over confidentiality or GDPR. So if you could move on to the next slide, please, David, thank you. But firstly, before that, for those that aren't familiar with us, we just wanted to introduce the project partners and team that are undertaking the project. So it's led by AECOM. We're a global engineering and environmental consultancy working across a wide range of infrastructure and development markets. In the UK, we have ongoing active involvement in carbon capture and other energy transition and renewables technologies. We offer a variety of technical consultancy services in relation to carbon capture and have worked on many UK projects helping developers and site owners develop carbon capture, as well as developments overseas. We've had a number of members of the AECOM team on the call today, some of whom will be leading parts of the meeting, including David Menmuir, Clem McKenzie, Stephen Florence, and Kevin Taylor, who's part of our US-based specialist process engineering team. AECOM is supported in this study by the University of Sheffield, and specifically John Gibbons, who is a professor in carbon capture there. Many of today's attendees will know John, and that he's had a long career in carbon capture and energy technologies. He's also been a director of the UK CCS Research Centre since 2012 and is involved in the Turk test plant that operates out of the University of Sheffield. We've worked with John on previous BEIS projects, and his knowledge and perspective are helping to guide the direction and outputs from the project. The UK CCSRC are also supporting the project, as you'll know from registering for this call, and Caris Blunt and Vic Giordano Bibby are working behind the scenes today to make sure that the presentations run smoothly. We're also, of course, working very closely with the BEIS Carbon Capture Innovation team, and we have Nick Bevan and John Gordon, I think, on the call today. Hopefully you'll see them pop up in the discussions as we go through the afternoon. So if we move on to the next slide to quickly run through the overall study objectives. The overall objective of the study is to support BEIS's policy and decision-making on innovation funding for next generation carbon capture technologies, and in particular to inform call 2 of the Innovation 2.0 programme in May this year. More specifically, the study will undertake a review of next generation technologies as they apply to industrial, waste and energy sectors, and develop a techno-economic analysis of a range of technologies and applications to provide a comparison against a state-of-the-art benchmark which for the purposes of this study we're considering to be an amine solvent post-combustion technology. Alongside this, BEIS wish to understand the applicability of next generation carbon capture technologies to different industrial sectors, and help UK industry understand the next generation carbon capture technology, engage with industrial sites to understand site-specific challenges and costs in deploying these technologies in different applications, which is where today's workshop and other stakeholder engagement activities come in. The study is focusing on the most mature next generation carbon capture technologies, hence those that we're focusing on in the techno-economic analysis will need to be at a TRL. That means they have the potential to deploy on industrial sites at full commercial scale from around 2030 where possible. By full commercial scale, we're considering an order of magnitude of around 1,000 tonnes of CO2 capture per day, but the actual scale is subject to the application of the technology. And just to confirm, the study is not considering CO2 transport and storage, and we're not considering hydrogen production, as those are the subject of separate work within BEIS. So if we flip to the next slide, thanks. David, this illustrates how those objectives will be met through the scope of the project. So the various work packages that constitute the study works are shown in the boxes along the top, and those boxes represent work packages 2, 3, 4, 5, and 6 that I'll talk about shortly in a bit more detail. And at the bottom is an indication of the range of technologies and applications that are being considered in the study, from non-amine solvents, solid sorbents, membranes, fuel cells, alum cycle, and direct separation technologies in various processes. And also looking at the direction of travel for more established amine solvent technologies. Excuse me. The range of sectors covers the main energy intensive industries in the UK, from power generation, from natural gas, biomass or waste, to cement, glass, refineries, iron and steel, etc., with the industry specific issues and constraints associated with them. A couple of things to point out on the scope on this slide. The technology review, which is covered by work package 2, looked at technologies likely to be available at commercial scale by 2030, as I said, and in work package 4, that covers the case study, which we're now calling a pre-deployment verification unit, which is part of what we're going to discuss later in the call. So moving on to the next slide, I'll just run through quickly where we're at on each of the work packages as we work through the project. We kicked off in August last year, and as I say, the completion is anticipated to be in April this year, in time to inform the call to funding call. So for work package 2, the technology review is complete and has been updated following the first stakeholder engagement workshop. An interim version of this report will be published on the UK CCSRC website this week. We'd encourage everyone please to have a look at that and provide any comments you may have. The link to the web page is the same as the one you used to register for today's event, and we'll show that again towards the end of the presentation. We'd also point out that on the work package 2 report, it's intended to be an update on previous BEIS and IEA GHG work, and there are obviously a very large number of early stage and bench scale technologies in development. We may not have covered all of those in the report, but the principal objective for the review is to identify those with the greatest potential for commercial scale deployment in the next 10 years or so, and so that's the main focus of the review and identification of technologies. Regarding work package 3, today's event is the second of 2 workshops of this nature, but we would welcome any further comments or representations regarding the study from stakeholders, those attending today or others with an interest in the outcomes of the project. We would say, though, that if possible, these and comments on the interim reports should be directed through the industry and representative bodies that make up the advisory board for the project, just to kind of make things a bit more manageable. We'll also, as I said, talk about work package 4 later in the call, but a draft configuration report has been issued to BEIS for that, and that will again be published on the UK CCSRC website this week. That report will be completed and updated based on feedback received from today's workshop and subsequent comments received to finalise that. Similarly, the interim methodology report for the benchmarks and techno-economic assessments will be published this week, and we'll discuss the benchmark and next generation configurations that we're considering studying later on in the call. The methodology report summarises the overall approach to modelling and economic assessment that we're using in the study, including data sources for utilities costs, hurdle rates, and so on. So we'd very much appreciate feedback on the applicability of the proposed data sources and assumptions as they apply to your site or application. Development of the benchmark models that will form the reference for the next the techno-economic assessment of the next generation technologies is ongoing. Work package 6 is just getting started in Anger at the moment. We're in the process of finalising with BEIS the technologies and applications that are to be assessed in the techno-economic model. And we've also been canvassing the relevant technology providers to seek data on their processes to support that assessment. So that's everything we wanted to say as an introduction to today's workshop. And so if we move on to the next slide, I'll just recap on the main objectives for today's call. As I said in the agenda, the two main parts of today's call will firstly be to provide presentation from companies developing next generation technologies, to give information on the nature of the technologies and their application, and then to outline the pre-deployment verification pilot plant concept. What we really hope to achieve on today's call is to generate as much feedback and open dialogue as we can on the various complex and interrelated issues associated with these projects. So if you have any thoughts, observation, comments or questions as we run through the presentation, please can I ask you to put them in the meeting chat. I suspect there's too many people on the call today to throw the floor completely open. So when we get to the feedback sessions, John Gibbons will be chairing those, and he'll pick out sort of key points from the chat to start the discussion going, noting that we are time limited. So before we move on, we would just like to get an idea of the numbers of people representing the various interests among the stakeholders attending today's call. So Karis will shortly be putting a question up on the screen to ask people to identify yourself sort of by category. So if you could please click the appropriate answer and then click submit, that will help us to give some context to the responses to the questions that we'll be asking later in the call. So with that, that's sort of the completion of the introduction. I'll hand you over to David Menmuir, who's going to introduce the proposed benchmarks and technologies, and then run us through the developers' videos. So thanks very much, and over to you, David.
Okay. Thanks very much for that introduction, Andy. Yeah, this section of the presentation will talk a little bit about the benchmarks we're using in our techno-economic assessment, then about the next generation technologies, and the main part of this section is this technology supplier videos which we've received, which should be quite interesting, just showing their take on the technologies that they're providing. So when you're conducting the techno-economic analysis, you're looking at these different next generation technologies, and you're trying to do some calculations on things like the cost of capturing carbon with them. And when you're doing the comparison, you want to have benchmark scenarios so that you can think, are these new technologies better? Are they cheaper, or are they offering other advantages, or do they have other challenges? So for this study, for the benchmarks, we've used amine solvent technology, and you can see a simplified diagram of the amine solvent process on this slide. So the amine solvent has been selected because it's, I'd say, fairly well regarded as one of the more established carbon capture technologies. It's been used for many decades in the oil and gas industry for removing CO2 from natural gas. There's also a number of projects in different industries around the world capturing carbon using amine technology, including some of the really big ones you may have heard of, projects like Boundary Dam and Petronova, which are large power generation applications using amine solvent capture. In the techno-economic analysis, we've got the amine capture attached to 3 different base emitters. So these are gas power generation, energy from waste, and cement manufacture. Now, these industries have been chosen for a number of reasons. One, because they're quite likely candidates for carbon capture. And the other reason is because they're seen as quite representative of a broader range of industries. So the scales, the flue gases, and some of the integration challenges are similar to ones that will be experienced in different industry sectors. So an example would be, if you're operating a biomass power plant, it's got a lot of technical similarities when you're adding carbon capture to an energy from waste plant. So the idea is that by selecting these 3 industry sectors, the results will be applicable to a broader range of industries. So for the next generation technologies that we've been looking at in this study, this table shows a list of them. Just to run through really quickly, you've got improved amines, rotating absorption systems, solvent systems that aren't amines, non-amine solvents, solid sorbents, fuel cells, membranes, the alum cycle, which is just for gas-fired power generation, and direct separation reactor technology. Now, this is mainly at this point in time for lime and cement production. So the first thing you notice is there's lots of different technology concepts out there. And each technology concept has its own potential advantages and its own challenges. And it's important to remember that different technologies may be more or less suited to different applications. So depending on the scale of sites at your industry and the type of flue gas, and also other factors like the availability of heat. Some technologies use a lot of thermal energy. And if you've got a supply of thermal energy in your industry, then that might be a good technology. If you don't, then it might make that technology less competitive. So if we could magically fast forward, let's say 10 or 20 years time, it might be really obvious that, I don't know, for making steel or making cement, you use technology X or technology Y. And if you're doing power generation, it's these 2 other technologies. But at this early stage of the carbon capture industry, it's not obvious. And particularly if you're focusing on your core process, to be presented with this different array of options can be quite bewildering. There's just a lot of different concepts. So one of the outputs of this study is to try to help industries and industry sectors narrow down the choices and think about which technologies may be best. So a few ways that we're doing this. There's the Work Package 2 report, which was review of next generation technologies that Andy mentioned earlier in the presentation. It should be quite good for providing a bit of sort of background education on these, or background information on these technologies. Certainly everything in this table we go through and we try to summarize the advantages, the challenges, and also the stage of development. So what actual plants have these technologies built so far? How big are they? And what flue gas were they treating? Another way of learning about what technologies might be good for what industry will be the supplier presentations that we're seeing today. Hopefully when the technology suppliers present, they'll give some indications of where they might see their technology being of most use. And finally, there's the results of the techno-economic analysis itself. This work's still underway. It's due to be published in May this year. But when this analysis is done, it will create a series of numbers about the cost of adding carbon capture to different industries. But there'll also be surrounding text that talks about things like key risks and important assumptions for the different technologies. So this should provide a useful starting place for narrowing down options for carbon capture technologies in your industry. Okay, so before we get on to the videos, there was 3 technologies where there aren't videos for. Now, we have asked these suppliers for videos, and suppliers of these technologies for videos, and they may well come in the next days and weeks. If they are provided, they'll be uploaded to the UK CCSRC website, and you'll be able to access them there. But in the meantime, I wanted to say just a few words on these technologies today because they are potentially important in the future, and it means that they're covered in this workshop today. So advanced amine systems, really what this means is taking current amine carbon capture and improving it through incremental improvements. When the suppliers are building these projects, they will learn in the process of building them, and they'll see ways for them to be improved. So these could be things, it could be changing the chemistry of the amine solvent or adding additives to improve performance. It could be the way that the solvent's managed, or it could be something like the thermodynamic design of the process, which would allow less energy to be used, or even things like construction techniques which will bring down capital costs or make the plant more reliable. So this is basically to say that amine systems are currently reasonably well developed in some applications, but it's not to say that there's no further development possible. We fully expect that as these are applied, particularly in different industries, innovation will continue to happen and improve their performance. If we go into solid sorbents, in a solid sorbent system, CO2 is absorbed into a porous material. So obviously that material can only take in so much CO2. Once it becomes saturated, there's a change in physical conditions surrounding that material. So in simple terms, usually the material is either heated or the pressure is changed, which drives off the CO2. The CO2 is released and collected, and then the cycle can start again and it can absorb more CO2. So the advantages, or some advantages of solid sorbent systems, is that they can avoid the use of a potentially hazardous solvent, and manufacturers will claim reductions in energy use. We have seen examples of pressure swing absorption and temperature swing absorption systems being used in other process industries. So there definitely is a precedence for them being useful gas processing techniques. So they could well find an application or a number of applications in carbon capture. As with any technology, there's challenges. I would say one challenge of note with solid sorbents is finding a sorbent material that doesn't degrade too fast and also isn't too expensive to buy. Because if your plant uses too much sorbent and the sorbent's expensive, then this will harm the economics, and then another technology may become a better choice. So that's one of the challenges of solid sorbents. So the last one before we go into the presentations is membranes, which you'll see an example of membranes in the photograph. Again, they avoid the use of a hazardous solvent. They're obviously modular, so they can scale up to different sizes. Because of the way they work, they have a good turn down ratio, if your process isn't always running at a constant output. You don't have thermal energy required, which is useful if your site doesn't have easy access to low carbon thermal energy. And we have already seen some of these in the application of upgrading biogas from anaerobic digestion into biomethane by removing the CO2. There's already membrane systems being commercially used. One challenge with membrane systems is in some instances, they struggle to achieve a high capture level. So if you're looking to capture, let's say 95% or 90+% of your CO2, membrane systems may struggle if that's one of the objectives of your carbon capture system. Okay, so this is the technology provider presentations that you'll be seeing today. When we asked the technology providers to make these presentations, I would say it was a fairly open brief. We basically said, you've got 5 minutes and we want an introduction to the technology. We want to know when it might be used, and we want to know about why it's good. Why should we buy this technology? What are its advantages? So it should be very interesting to see the results that come back. One final point, as these videos will play through, for the 8 Rivers one, which is the alum cycle, we think there's a technical problem with the sound. The first 30 seconds or so of the video don't have any sound, and it certainly looks like it should. And there's a bit at the end of the video that also doesn't have sound. So we have requested an updated video, which I expect we'll get, and it will go on the 8 Rivers on the website. But in the meantime, for the purposes of today, don't worry if you're not receiving sound at the start of that video. It's not a problem with your computer. Sound will just come on after 30 seconds or a minute or something like that. And yes, we'll have time for questions and discussions after these videos.
The mission of Cyclone CC is to achieve $30 cost of carbon capture, especially for hard to abate industry. And we're doing this by doing 2 things. One, we are utilizing process intensification and intelligent engineering to compress the size of carbon capture unit by 10 times. And secondly, we are utilizing our proven patented APPS solvents to achieve a 50% operating cost reduction. And when commercialized, industrial companies and customers will be able to install these units in less than 8 weeks, highly improving their operation profile and any downtime our customers may face.
Carbon capture, utilization and storage has the potential to decarbonize the economy and maximize economic opportunities. High costs are a significant barrier to adoption, a problem being solved by Carbon Clean. We have successfully pilot tested and are now commercializing at 10 tons per day and 100 tons per day with select partners who will work with us to gain advanced knowledge for final product rollout by summer 2022. Cemex and Veolia are among our champion partners.
Cyclone CC is a breakthrough combination of 2 process intensification technologies: Carbon Clean's advanced proprietary APPS solvent and a novel process technology called rotating packed beds, or RPBs for short. RPBs are a process intensification technology that improve the absorption of CO2 into the solvent. At its heart, an RPB contains a disc of packing material which rotates about its axis. This generates a centrifugal force within the packing, which enhances the CO2 absorption process. The solvent is introduced into the RPB at its centre, where it's sprayed onto the packing via a liquid distributor. When the solvent contacts the packing, the centrifugal force applied to the solvent from the rotational motion forces the solvent to travel radially towards the outer edge of the packing, where it drains down to a sump before being pumped to the next stage of the process. The flue gas is introduced to the RPB from the outer edge of the packing and exits at the inner edge, where the solvent enters. Therefore, the gas and the liquid contact each other in a countercurrent fashion. The flue gas is absorbed by the solvent, and the CO2 present selectively reacts with the active components in the solvent, thereby temporarily locking the CO2 within the solvent.
Doosan Babcock have been delighted to host and support Carbon Clean in the development of their next generation Cyclone CC technology at our carbon capture test facility in the UK. Carbon Clean's Cyclone CC modular technology allows a significant reduction in equipment size. This allows the deployment of technology in sites where space is constrained or limited. It also potentially enables as much as a 50% reduction in CapEx and OpEx compared to other plant designs. We look forward to continuing our support to Carbon Clean as they continue to develop and commercialise what is an extremely exciting technology.
As governments take greater action to incentivise the transition to a sustainable economy, they have recognised the vital role carbon capture utilisation and storage, CCUS, has to play. The International Energy Agency state that CCUS can reduce global emissions by nearly 20% and the cost of mitigating climate change by 70%. We are working with more companies than ever. Cyclone CC enables scalable, cost-effective carbon capture and has a crucial role to play in helping hard-to-abate sectors decarbonise and more broadly keep average temperature rises to below 1.5 degrees Celsius.
Hello everybody, my name is Johan Ljungholm. I am the head of business development for Co2 Capsule and based out of Oslo, Norway. We are bringing a highly competitive and proven carbon capture technology solution to market and would like to share that with you today. In order to reach the UN's climate goals, carbon capture must be increased 100-fold in the next 30 years. This, of course, will require a lot of investment, and as part of that solution, Co2 Capsule offers a highly competitive and a well-proven carbon capture solution using hot potassium carbonate. The CO2 capsule process is based on a traditional hot potassium carbonate process with a few additions that will maximize the efficiency of the absorption-desorption process. In addition, we do introduce an energy circulation and recuperation system within the system that allows us to reduce the cost significantly of carbon capture. This system also allows for the utilization of electricity alone in cases where steam is not available, which is a large advantage. But for optimization point of view, you can also use process heat or steam from the mother plant. You can also, in addition, integrate the heat recuperation cycle that we use on the desorber side from the liquefaction process in order to get some of the energy back from there. And at the same time, we can also optimize the system to recuperate heat and add it into, for example, district heating. The system itself is quite simple. It compresses the flue gas coming out of the mother plant. The compressed flue gas is introduced into the absorber where it is mixed with the lean hot potassium carbonate solvent. The hot potassium carbonate takes the CO2 into solution, and the solvent, now saturated with CO2, goes into the desorber. At the top of the absorber, you had the cleaned, or I would say cleaned, it's about 90 to 95% of the CO2 removed at the top of the absorber, which in this cycle here, you can also recuperate some of the energy using an expander in combination with a compressor, so we don't lose too much energy. In the desorber, steam is introduced. Like again, the steam is produced within the system itself. It does not require external steam. And this is where CO2 is desorbed out of the solvent and pure CO2 comes out the top, while a lot of the energy required is recuperated within the system. We calculate an approximate energy consumption of 0.7 gigajoule of electricity per ton of CO2 captured, which is an approximate saving of OPEX about 15 euro per ton of CO2. The CO2 capsule technology is quite easy to integrate into an existing plant. It can be run on electricity alone if steam is not available. There's no reliance on any kind of specialized parts for this. It's all using standard components off the shelf. The unit capacity is approximately 2.5 million tons per year. However, it is very easily scalable both up and down. The solvent itself is quite safe. It's non-explosive as it is a stable salt, and also none of the byproducts have proven to be carcinogenic or in other ways being unsafe. It can be installed in between 18 to 24 months and does not require much downtime at all on the mother plant as it is an end-of-pipe solution. The industrial applications that we have seen so far is primarily in waste to energy, but in addition also biomass as a very large interest for this type of technology. In addition, cement plants where, for example, external steam is not available, steel mills, hydrogen, LNG, fossil power, and of course the process and chemical industry. The most recent case study is the Stockholm Exergy selection of CO2 capsule technology. This was based to a large extent on the highly competitive economics of the system, the ease of installation, the proven technology using hot potassium carbonate, the safety aspects, since this is located in the center of a major city, and the opportunity to recover a lot of the energy cost from the carbon capture process into district heating. This plant itself in Stockholm will capture 800,000 tons of CO2 per year, and it will be commissioned in 2025. On behalf of all of us at Co2 Capsule, I want to thank you all for the opportunity to present our technology today, and good luck with all your CO2 capture ventures in the future.
Welcome to our 5-minute introduction to C-Capture's unique next-generation carbon capture technology. C-Capture is a small but rapidly growing UK technology startup based in Leeds. Our core technology revolves around a novel, patented, non-amine CO2 solvent technology, which was originally invented at the nearby university, from whom we originally span out. When combined with our optimized process design, we believe that this technology presents a step change to the current CO2 solvent-based capture technologies currently available in the marketplace. The technology itself has been developed over the past few years through a combination of UK grant funding and our external investors, IP Group, BP, and Drax. In summary, our technology provides 3 key areas of differentiation. Firstly, the physical nature of the solvent and the underlying chemistry is significantly different than that found in conventional amines. This dramatically reduces the amount of energy needed to capture and release the CO2 by up to 40%, resulting in significantly lower plant operating costs. The solvent itself and its degradation products are both low in toxicity and environmental impact, which, when compared to amines, leads to significant benefits with regards to operations, waste management, and in particular, process emissions and permitting. The solvent is also very robust to high levels of conventional contaminants, resulting in low solvent degradation and losses. And as such, this is ideal for application in hard-to-abate sectors such as steel, cement, waste-to-energy, and glass applications. Our technology proposition is simple and based on a similar absorber-desorber process flow scheme as you would find in a conventional amine solvent process, but with a few key differences. Our solvent is tolerant to contaminants such as oxygenates, particulates, NOx and SOx, minimizing solvent degradation and losses. It has a very low foaming behavior, which reduces process upsets. And carryover is not affected by high particulate loadings. Our solvent is readily recovered from our flue gas streams, which minimizes emissions into the atmosphere. And any emissions that remain have both low toxicity and environmental impact. As well as being robust to contaminants, the solvent is also low in corrosivity, enabling lower cost metallurgy in some key parts of the plant. And in addition to our process requiring significantly less steam when compared with amines, our solvent is also more robust to heat degradation, enabling the desorber to run at higher temperatures if needed, which enables pure CO2 to be delivered to the compressor at around 4 or 6 bar and eliminates the need for first stage of compression. Or alternatively, the process can also be run at lower temperatures, enabling integration with district heating opportunities. As mentioned previously, our current focus for this technology is for application on hard-to-abate sectors. However, we believe it's also applicable across the broad spectrum of industry CCS applications as a whole. Our initial strategy is to concentrate on post-combustion flue gas streams with CO2 content greater than around 8%. However, we have also identified programs in place to further expand our technology focus to cover more challenging, leaner CO2 applications as the technology matures. 2022 will be a really important and pivotal year for sea capture and our technology. Following on from our previous prototyping activities, we are currently installing and will be operating our latest fully integrated 1 ton a day pilot facility at Drax during the first half of this year, which upon success will enable us to start openly licensing the technology on a commercial basis from Q3, Q4. We're currently working with a number of companies and seeking further opportunities to work with others to support us on our commercialization pathway. Our next key target is to identify an intermediate scale plant of around 100 or 200 tons a day for startup in or around 2025. This plant will provide us with the stepping stone needed to then roll out at larger commercial scale and across a number of industrial sectors to help to support the massive CCS challenge which we as an industry are currently facing. My name is Phil Southerden and I am the Chief Technology Commercialization Officer for Sea Capture. If you would like to understand more of our technology or would like to be part of our journey, please contact me or visit our website for more information. Thank you very much for listening. I hope to hear from you soon.
My name is Hossein Gezelak, and I'm pleased to be presenting the next generation carbon capture technology based on carbonate fuel cells developed by Fuel Cell Energy for simultaneous carbon capture, power generation, and hydrogen production. Founded in 1969, Fuel Cell Energy has developed environmentally responsible products for distributed power generation, distributed hydrogen production, and carbon capture solutions, which are trademarked short source based on carbonate fuel cell technology platform. Let's look at how short source cell works. As shown in the figure in the left, each short source cell has two compartments similar to a plate fin heat exchanger. One of the compartments is the cathode, where the CO2 bearing flue gas is fed. In the cathode, one molecule of carbon dioxide reacts with half molecule of oxygen and absorbing 2 electrons to produce a carbonate ion. The negatively charged carbonate ion migrates from the positive cathode to the negative anode, which is the second compartment in the short source cell. The carbonate ion reacts with hydrogen in the anode, producing 1 molecule of carbon dioxide and 1 molecule of steam. This oxidation reaction process releases 2 electrons that flow in external circuit to produce electric power. Hydrogen is produced by internal reforming of fuels such as natural gas within the anode compartment, where specialized reforming catalysts are placed. The configuration of a single short source cell is shown in the bottom of the slide. As an overall process, short source cell transfers carbon dioxide from cathode side to the anode side, that is the fuel side. It accomplishes this carbon dioxide transfer with complete selectivity towards carbon dioxide as compared to nitrogen in the flue gas. The net result is a concentrated stream of CO2 exiting the anode compartment. Therefore, the short source cell can be used as a carbon capture plant to separate CO2 from flue gas of other plants and simultaneously produce power. This co-production of power provides revenue stream to improve economics of the power plant. Additional benefits include flue gas NOx destruction and excess water production as a result of the chemistry within the fuel cell. Efficient conversion of methane fuel to hydrogen in short source provides capability for hydrogen co-production and the opportunity for hydrogen export. Short source fuel cells are manufactured in fuel cell energy facilities from single planar cells to stacks of 400 cells to a finished 1.4 megawatt power module ready to be transported to the customer site. Let's look at the operation of the entire short source carbon capture system. A simple process block flow diagram of the carbon capture system is shown in this slide. The CO2-rich flue gas from a power plant or industrial site is shown in the green color at the bottom of the diagram. This flue gas is first heated using the waste heat from the system. The heated flue gas, shown in an orange color, enters the short source cathode, where up to 90% of its CO2 is stripped off, forming carbonate ions. The remaining CO2 depleted flue gas flows to a heat recovery system where its sensible heat energy is used to heat up the fuel and vaporize water to make fuel-steam mixture with a carbon-to-steam ratio of 2 for natural gas-based systems. The CO2 depleted gas is finally exhausted from the system. The humidified fuel, shown in dark blue color, enters the short source anode, where it is internally reformed to form hydrogen. The produced hydrogen converts the carbonate ions to carbon dioxide. The overall electrochemical reaction, as mentioned before, produces water and makes the stream rich in CO2 and some remaining hydrogen. The overall process also makes electricity that is exported to the grid. The outlet of anode exhaust is first cooled down to remove the water content of the CO2-rich stream, and then is compressed and chilled in a chiller to separate pure liquid CO2 as the carbon which is captured. The remainder of fuel stream is highly concentrated in hydrogen. Now, there are two options for using the hydrogen produced from the carbon capture system. One is to recycle the hydrogen back to the system to increase the overall efficiency of electric power generation capability of the short source carbon capture. The second alternative is hydrogen to X, using a small final PSA system to strip off pure hydrogen from hydrogen CO2 mixture. So, as discussed, the overall short source carbon capture system is capable of capturing in excess of 90% of CO2 from the subject flue gas while producing power simultaneously. Plus, it provides an option to produce pure hydrogen for export. One other attractive feature of the system is being water self-sufficient. The plant actually produces excess processed water that can be beneficial to the power plant or the industrial site. The economic benefit of short source capture technology is due to the revenue from additional power produced by the fuel cell, offsetting the operating cost of the system, resulting in a low cost of carbon capture. I would like to thank you for your attention to my presentation. For further inquiries about short source carbon capture systems, please contact me through my email address hkazal@fce.com.
To reduce CO2 emissions, power plants layer on complex processes, resulting in increased electricity costs. Net Power breaks this paradigm, using a clean sheet approach to design an efficient, inherently emissions-free power cycle. Net Power uses supercritical CO2 instead of steam to produce power. Natural gas is combusted with hot, recuperated CO2 and oxygen, preventing NOx production. Burning with oxygen, known as oxycombustion, is typically uneconomic because oxygen is expensive to produce. Net Power overcomes this problem by recuperating the majority of the produced CO2 into the combustor, dramatically lowering oxygen requirements. The resulting working fluid of high-pressure CO2 and water is expanded through a turbine and then cooled in a heat exchanger. Water is removed, and the remaining nearly pure carbon dioxide stream is compressed and pumped back to high pressure. Excess pipeline-ready CO2 is exported before the working fluid is reheated in the heat exchanger and returned to the combustor. This breakthrough process produces low-cost electricity, eliminates water consumption, and is emissions-free.
My name is Rodney Allen. I'm one of the inventors of the Net Power alum cycle system. Everybody is anxious to preserve the climate and preserve the environment, and it's one of the most pressing issues globally, is to get sustainable use of energy in the future.
Back when we first created this technology, people looked at us like we were nuts, like it was too good to be true. We have a giant CO2 heat pump that we tested here outside of Houston, Texas. The summer of 2018, we lit it and it worked. And the world realized things changed.
I'm Brian Murray. I'm the director of the Duke University Energy Initiative. You know, I've seen a lot of other power plants in the world, and you have this image of what one looks like, and this looks like something completely different.
The problem is not fossil fuels, it's disposal is the problem. It's putting it in the right place. We make sure that the CO2 is valuable, not valueless, because it has no value right now. It's very easy to vent it to the air. But by creating value for that CO2, it makes it irrational to throw it away. It makes it totally rational to capture it and to use it.
So Net Power could be a game changer by essentially lowering, if not eliminating, the trade-offs between low cost and clean. If it can produce electricity at a cheaper cost than the incumbent technologies, natural gas combined cycle, coal, nuclear, then the market is going to drive it towards that. And if the market drives it towards that, and it's produced this significantly cleaner form of electricity, that's going to be the kind of thing that isn't going to require big policy imperatives from Washington or for state capitals. The market can drive it, and that ultimately is their hope.
Hello, I'm Tom Hills, and I'm going to talk to you today about the Lilac technology for capturing process emissions from the cement and lime industries. Cement is used in our roads, buildings, homes, offices, and almost all our infrastructure. Lime is used in a variety of applications, including the iron and steel, chemical, paper, pharmaceutical, drinking water, food, and farming industries. However, the cement sector is responsible for 8% of global CO2 emissions. The majority of CO2 emissions are released directly and unavoidably from the processing of the raw materials. The Lilac Group aims to apply a breakthrough in low-cost carbon capture technology that will enable the cement and lime industries to reduce their emissions dramatically while retaining their international competitiveness by capturing those process emissions at low cost. The Lilac technology simply ensures that the pure CO2 released from the processed materials is not contaminated by flue gases or air. Heating of the process occurs in a furnace which surrounds a steel tube down which the limestone or cement raw meal falls. The hot steel walls radiate onto the powder, causing it to calcine, releasing its CO2. The resulting gas is almost pure CO2, which is removed from the top, and the calcined powder continues to the bottom, where it is removed and sent to the rotary kiln in the case of cement, or a cooling stage in lime manufacture. Lilac requires no new processes, which may have their own energy penalties. It introduces no new chemicals either. It can use virtually any fuel, including fossil fuels such as natural gas and coal, alternative fuels such as RDF or SRF, or emerging low-carbon fuels such as biomass and hydrogen. Lilac is unique in that it can use electricity as the thermal fuel, offering a viable, near-future solution for electrification of cement and lime plants. Here we can see how Lilac would fit into a cement plant. On the left is a conventional cement plant with a precalciner between the preheaters and rotary kiln. Lilac replaces the precalciner, and maybe a couple of the preheaters, and generates a calcined meal of suitable specification, that is, around 85 to 95% calcination, depending on the requirements of the rotary kiln. This design can be retrofitted and in a modular approach. Calyx and our partners are undertaking several development steps to bring Lilac to market as swiftly as possible. The first was Lilac 1, a Horizon 2020 project started in 2016 and completed in June 2021. We built a pilot on Heidelberg Cement's Lixer plant in Belgium with approximately 5% of the capacity of the host plant. It was built on time and on budget in 2019 and can capture up to 95% of the processed CO2 at 95% purity. We were unable to get to full capacity due to ancillary issues around the product conveying and furnace, but the core process worked extremely well. As a result, we launched Lilac 2, another Horizon 2020 project, in April 2020. Whereas Lilac 1 focused on the process inside the Lilac unit, Lilac 2 has more focus on how the technology integrates into a cement plant. As such, we are planning to burn the same fuels as are used on the host site, this time Heidelberg Cement's plant in Hanover, Germany. Preheated air from the clinker cooler will be used for combustion, and heat recovery will be performed in the preheaters above the Lilac module, which has 4 times the capacity of Lilac 1, i.e. 20 to 25% of the capacity of the host site. This is equivalent to capture of 100,000 tonnes of CO2 per year. The calcined meal will be fed into the kiln too, proving the suitability of the technology from a material specification point of view. As mentioned above, Lilac's techno-economics are compelling. Including capital costs and compression, we expect avoidance costs of around €20 per tonne of CO2, assuming the plant runs on RDF, as shown on the left of this chart. A major advantage of Lilac is that, unlike other technologies, it generates little extra CO2, reducing the total amount of CO2 that needs to be captured and stored per tonne of CO2 avoided. This is apparent when comparing to amines, which is shown in the middle 2 bars of the chart. As we have discussed, Lilac captures only the process emissions and not the combustion emissions. However, its lower cost means that applying Lilac for process emissions and building a smaller, cheaper solvent plant dedicated to the combustion emissions, if a carbon-emitting fuel is used, is significantly cheaper than relying on solvents for both. Lilac has another option for realizing net zero cement and lime manufacture, the use of zero-carbon fuels. This could be sustainable biomass, hydrogen, or even renewable electricity. As part of Lilac 1, we developed a technology roadmap, which is a good read and available at the link shown on the screen. Thank you for your attention, and please don't hesitate to get in touch if you have any questions.
I was just going to introduce John Gibbons, hopefully is on the call somewhere. I think John was going to lead the discussion following on from the video. So if you're... Yep. Hi, John. Right.
Hi. Yes. Okay. Let's have a look at the chat. So we don't have many questions in the chat, but we do have some clarification questions going back actually to the earlier section. a question about which amine is used for the benchmark values. Andy, do you want to address that?
Sorry, I'll just put my video on. Yeah, so as I said in the chat, in my response in the chat, yeah, the intention is that the benchmark will be based on kind of representative performance for typical proprietary amine technology. So we're not looking to model a specific amine technology, but it'll be a kind of representative performance as the benchmark. So we have models, also have models based on MEA as open source technology. Open art technology, so that'll also inform the amine benchmark against which the techno-economics of the next generation will be compared.
Okay. And another question, I don't know whether there's anybody from Sea Capture here, but there's a question about solvents used in the Sea Capture process. Anybody?
Hi, John. Phil Sutherland here from Sea Capture.
Oh, great.
So I can answer that very, very, very simply. It's obviously it is our proprietary solvent. So the makeup of that and the kind of our secret ingredients is not something that we would like to share, but I think it's more around what is not in the solvent. We have no nitrogen species, hence any amines are omitted from our solution. If that answers the question, then otherwise I can expand a little bit if you want to.
Please.
Okay, we have no amines, and it's made from very standard kind of commodity products. And the other area is it's consists of hydrogen, carbon, and oxygens only. And that's if people would like to understand more, then by all means come to Sea Capture and we can talk in more detail, but under confidential restrictions.
Okay, that's very good. Thank you. Another question about fuel cell energy and the acceptable CO2 content in the flue gas. Is anybody from fuel cell energy on the call? Anybody from AECOM want to answer that, or anybody else?
I was just going to ask actually if Kevin's on the call, if you're able to answer that. I know you've worked with fuel cell energy.
Yeah, I've worked with fuel cell energy. I thought Hossein was on the call, but I guess he's not jumping in at this point. But the fuel cells work over a pretty wide range of CO2 concentrations. So they do tend to work better at the higher concentrations. So things like cement or energy from waste, the 10, 12+% seems to work a little bit better if you're trying to get to over 90% capture, although you can design for natural gas combined cycle, power plant type flue gases as well.
Okay, thank you. And then a question, which of the technologies would potentially be applicable for direct air capture and why? Okay, Andy, do you want to sort of give a disclaimer on that one? And does anybody want to talk about direct air capture for their process?
I don't know if you have any takers from the presenters on that, but I guess that, yeah, obviously the fundamental issue with direct air capture is the CO2 concentration is very low. So as we just discussed, some of the technologies favour higher CO2 capture rates. John, I think you probably know more about direct air capture than I do, but that would be kind of.
Well, none of the technologies I think are particularly intended for it in the present configuration. I mean, people are looking at using amines potentially. People are certainly looking at using lime that's produced with CO2 capture to then remove CO2 from the air by one means or another. Anybody from Lilac here, has that been looked at?
Yeah, I've got my hand up, but I don't think anybody's noticed.
Oh, sorry, I can't see everything all at once. That's the problem.
It's a really good question. What I would say straight away is that there's a document from the European Lime Association which points out that given how lime is used, roughly 33 an amount of CO2 is absorbed in in processes that's between about a quarter to a third of the total process emissions, just in the routine use of lime in these various different applications. So there is some form of capture there. Some of it will be from the atmosphere, some of it's from other processes. Of course, there's the soda lime process for direct air capture as well. So although we don't have the soda part of the technology, there is the lime part of the technology there. You could do direct lime capture, or you could, even lime the oceans. People have talked about that. But yeah, like you say, John, it's not a direct application that's being looked at for application in the next 5 or 10 years. There's a few more steps to go before then.
Okay, anybody else got any more comments on that?
This is Kevin Taylor again. I've looked at a few direct air capture projects, and I would say the leading contenders for commercialization at this stage are different technologies than the ones that we look at for point source capture. They're sort of similar to, a lot of them are solid sorbents, so they may be similar to some of the solid sorbents that are being considered for point source capture, but they're slightly different applications or technologies.
Okay, I mean, it certainly wasn't in scope for this project, which is looking at capture from essentially industrial sources of one type or another. There are other BEIS research programs on direct air capture. Nick, do you want to say anything about those just very quickly? I know we're getting a little bit off topic.
So we will be publishing the reports for the phase 1 of the direct air capture and greenhouse gas program, and they're looking to move to phase 2 after that. So something very much, but for this study we deliberately didn't focus on direct air capture because that's very much their area of focus.
Okay, another question: were people looking at essentially, I guess, a carbon black production process? I'm not familiar with the actual process itself. Andy, did we look at any pyrolysis or carbon CO2 conversion processes?
I was going to direct that question to David, actually, who led the production of the Work Package 2 report, where we screened all, a wide range of technologies. So, there are quite a number of earlier stage development technologies that are referenced and identified in that Work Package 2 report that hopefully people will see when they look at it on the UK CCSRC website, but that haven't gone sort of through to through the screening for kind of 2030, 35 deployment at the scales we're talking about. David, I don't know if you have any more to.
Well, the short answer is it certainly wasn't one of the main ones we looked at. There was they were split into different categories depending on what stage of development they were at and how close they were to being able to do 1,000 tons a day, and it certainly wasn't in the top two categories.
Okay, I don't know, Tim Rowe, are you on the call? Do you want to say anything else about that? I mean, are you considering that process for a commercial application yourself?
No, we're not considering it for a commercial application. It's just something we stumbled across, and we were interested to know whether it got any visibility in the UK to date. But I suspect it's still too early on in its development process.
Mm-hmm. Okay. Question from Abdulaziz on the capsule technology. 0.7 gigajoules of electricity per ton of CO2. What was your question on that?
Hiya.
Yeah. What was your point about the capsule energy consumption?
I just wanted to have an understanding if they could kindly elaborate how they reach 0.7 gigajoules of electricity per ton of CO2 captured.
Anybody from Capsule on the call who'd like to talk about that?
Abdul, they have good presentations on the CO2 Capsule website. If you wanted to hear a bit more about them, a bit more about the underlying process and some of the design work they've done, you know, in the run up to the Stockholm Exergy project.
Just a comment. I think in the report it said they didn't necessarily need to use heat energy. If you're working with an amine with steam extraction, then you lose about a quarter of the electricity in providing the heat, or so 0.7 gigajoules in that ratio translates to 2.8 gigajoules of low-grade heat. So it's not as different as it might seem in some respects. Svante technology, it's not, we're not running a panel. I think, are we planning to include Svante in the assessment, David or Andy?
So certainly in the work package 2 reports, Svante has been written up. So there's some text in that report which will be published shortly, just on the advantages and the challenges and what the technology's done so far.
Yeah, so I think the answer is gone.
Yes, sorry, I was going to say, yeah, a solid sorbent absorption technology is likely to make it through into the techno-economic assessment, although as I said earlier on, we're sort of finalising kind of the scope and list of those with BEIS and with Nick at the moment. But yeah, appreciating that within that technology, the actual sorbent that's used will be dependent on the application and the specific flue gas. So that's so the combination of the technology type and the application, or what we're trying to define with BEIS at the moment to identify exactly how, what technologies and how they'll be applied in the study.
So when we gave the brief to AECOM, we wanted to look at basic technologies that can have the capability to kind of scale up to the kind of 500, 1,000 ton a day kind of scale, and it's basically they're very applicable to industry, waste and energy sector, and hence ones that have already tested or have plans to test, kind of at levels between, so they're in good readiness to get to that level. We place more of an emphasis on that in the review.
Okay. There was a mention of biomethane upgrading. Again, I think that's out of scope for this project. Is that right, Andy?
Not specifically, but in terms of applications, biomethane is covered, and we do have some AD representation on the advisory board. So as a potential application, it's covered. Again, whether it makes it to the sort of the final shortlist isn't decided yet, or whether there's other technologies that or other applications that are kind of similar that sort of cover that. As David said in the earlier piece, also membranes are increasingly being used in AD technology. So yeah, it's a slightly different application to some of the other sort of combustion flue gas applications, but it's being considered, and where we're not actually studying specific case studies on a particular application, the final report will acknowledge them and acknowledge the specifics of different applications and how the results of the techno-economic assessment of the various configurations that we do look at kind of apply, or how relevant they are to different applications.
And are we aware of any other of the technology providers advertising that they handle biogas? I can't think of anybody myself, but
I'm not aware of any others off the top of my head now.
No.
Yeah, so Carbon Clean's done a lot of biogas upgrading projects. It's where they develop a lot of their technology for. But I guess given how well kind of established some of the technologies already are in AD and biogas upgrading, I guess we focused a bit of our attention on some of the harder to abate sectors, or where there's a stronger need for stronger potential for next gen technology.
and a mention here from somebody about solid sorbents for biogas. Okay.
John, I think you missed Hillary's comment actually.
Oh.
Cost and time scale.
Oh yes. Yeah. Sorry. Thanks. Yes. Okay. Well, I guess anything that we're looking at in the track one order it's called is basically we're assuming that it's close to commercial deployment. Is that right, David? I mean, do you want to say how the technologies are being selected for the detailed studies in terms of readiness criteria?
Yeah, I mean, obviously being ready for commercial deployments dependent on a number of factors. If you there's some detail on this, Hilary, on the work package 2 report. It's perhaps not a satisfying answer, but before you'd make an investment decision on a large version of any of these plants, there's a whole lot of different aspects that would need to be considered. One of them would be the track record, and certainly at this point in time, some of the technologies, if you're wanting to buy one tomorrow, would indeed take a brave investor to do that. But it's elaborated more on the different specific technologies in that report.
So I guess on Hillary's point, a few of these companies are quite well established and have done numerous commercial projects. So they've definitely kind of got that capability. I guess the main gist of why we wanted to do this study is we know specific sites are thinking about their first sites for carbon capture, but also their kind of second and third, and are acutely aware of locking themselves into a certain technology. And actually, we wanted them to make sure they had all that available information about what is quickly maturing and getting ready to be commercially ready, for the for the beginning of 2030. And that's part of the reason why we wanted this study to be widely disseminated and to work with industry on this.
Okay. Also got a question about cryogenic technologies. Did we examine any of those, David? Oh, I guess, were those?
So again, cryogenic technologies gets a mention in the work package 2 report, but it's not currently on the short list for studies for the techno-economic analysis scenarios.
Yeah. So and then another question about carbon capture and mineralization technologies. Again, are they mentioned?
I would say carbon capture and mineralization technologies, probably I could say the same thing about it. We found with that, certainly so far, we couldn't find examples of anything that had really moved up the scale. So the technologies might have worked, but so far the examples we found were really quite small scale. The focus of the project was looking at things that were in the not too distant future, 1,000 ton a day type of scale. So we couldn't find anything that was going in that direction quickly for mineralization technologies.
Okay. All right, I think that's all the questions. I don't know how we're doing for time. Last chance if anybody wants to put a question in the chat.
I think that it does bring us bang on time actually to where we were going to move on to the work package 4 actually. So yeah, if there are any.
Okay, well, thanks for the questions, everyone. Handing back.
So I think now we hand over to Clint McKenzie, who's going to talk us quickly through the concept for the pre-deployment verification unit, and then we'll be asking some specific questions to sort of canvas views on that and how it applies to application in particular industries. So Clint, if you're there, I'll hand over to you. Thanks very much, and thanks John for marshalling the discussion.
Yeah, thanks Andy, and thanks John. So If we could have the first slide, please, which takes us on to kind of the agenda, and I'll just introduce you to the package, because for some people on the call, they haven't yet heard this before, and then talk through the objectives of this task and kind of the risks we looked at for the for this unit, which is essentially a de-risking unit for carbon capture projects. We'll have a quick look at the block flow diagram. The scale is quite small, so not going to spend too much on it. I'll just highlight some details and then move on into the discussion. So next slide, please. The overall objective for task 4, excuse me, is to provide a reference point for assessing next generation carbon capture demonstration plants that we're expecting to start seeking BEIS funding, and to establish a reference point for a CapEx and a program of what that might look like. So the reference we assessed comprises a de-risking unit for long-term verification, testing in operation under, and this is the important bit, and under the real conditions in situ at operating sites. So the proposed configuration for the de-risking unit concept is an amine plant with that it's a lot more mundane than some of the other technologies seen today. So it is meant to, in its base configuration, to be a retrofit to an existing energy from waste plant. However, rather than stopping there, the intent behind the design of this unit would be to easily modify the unit to adapt to individual sites' requirements, individual flue gases, and the flexibility to change the actual solvent that's being run within the unit. The package would comprise all the process equipment necessary to safely capture CO2 from a fraction of the site's flue gas, produce a testable CO2 product ready for either T&S or utilization, if available, and have the necessary emissions measurement equipment to monitor emissions from the de-risking unit process. So last but not least, the de-risking unit would be useful for testing real reclaiming strategies in situ. And this leads us on to the next slide, please. So we reviewed the capabilities and scales of existing test centers, and on the slide is just obviously just a limited summary, but I just want to draw your attention to the fact the scale of the different sites. I just want to draw your attention to that. You know, some of them are testing at 1 ton a day, some are a lot larger, like TCM, approaching kind of 80, 100 ton a day, depending on the flue gas. And they all have different approaches to solvent management and reclaiming. What we noted from our review, and so did the BAT review for the sector, was that coverage of long-term operation in one setup together with the intended reclaiming method for any particular site, that combination, it's kind of coverage of that is inconsistent, and on the whole, it's actually currently lacking, at least in the public domain. So next slide, please. The next slide really looks at the risks that we've identified and the purpose of the what we're calling the pre-deployment verification unit in addressing them. And at the top, we've got some showstopper risks, and really these are drawn from really severe consequences that potentially lead to post-combustion capture sites just shutting down. You know, the project has failed for whatever reason, and the consequence from a failed project may not necessarily stop at the factory gate. You know, it's recognizing that if major emitters don't feed into their transmission storage pipeline, then the system is underutilized, and there's an end risk to the government, because the government may end up paying for the shortfall in transferred CO2. So An example of such a risk could be if a few years down the line, a site finds that there are surprise emissions that they weren't prepared for being formed, and these are hazardous and kind of quite catastrophic to the project. If they don't do modifications, they just need to shut down. Or somewhat more mundanely, through identifying unexpectedly high running costs and kind of the economics of the project as a whole becoming unfavorable once they get a few years down the line, and they find that they potentially need to replace solvent more often than they expected, or they produce more waste than they expected. And in either case, having the de-risking unit there for an extended period of time would identify that issue on a small scale and allow you to put mitigation into place before you've committed to the investment in the full-scale plant, where the consequences of finding that out would be a lot larger. So the second category, these medium risks, it's less exciting things, and it is to do really with quantifying what is the real waste production rate and what waste is being produced and what is the uptime of the process on that particular site, on that flue gas, and so on. So really site-specific things. And it's informing the design with those more minor details so that you can put in place any additional cleaning requirements, or maybe some extra spare equipment to ensure that at least the uptime of the full-scale carbon capture plant is going to match that of the process that it's capturing from. Okay, and so that you don't end up with that perverse scenario where the main process can't meet its carbon capture obligations and its low carbon goals because the carbon capture plant is down quite often. So the last item is there are some potential marginal upsides that deploying a de-risking unit for an extended period of time may identify. And these are items such as identifying where the feed for the full-scale plant may end up being overly conservative, and so they actually don't need some of the design margins that they may have sought to deploy. Or highlights some, so that would highlight some potential value engineering for the detailed design phase. Or if you find, as you're generating waste, actually you would consider, there's no heavy metals in it, it's all relatively benign, and you can confirm that that waste is not hazardous, then that would be useful to know, at least to factor into the OPEX model, that you may not end up paying for hazardous waste disposal. Okay, next slide, please. So here's the block flow diagram for the proposed unit. As I said, don't worry about the text. I just want to highlight a couple of things. One, so pre-treatment and reclaimer units. Those are package items that different sites can readily configure, and the idea is that they have standard flange connections. So if you want to test a more complicated advanced solvent that needs a more advanced reclaimer package, and rather than going with just a simple pressure single stage reclaimer, you need something more sophisticated, you can swap that out and put in. Same with pre-treatment, including if you really want to test what would happen if you ran your site without pre-treatment. How much solvent would you really go through? So the second item to draw to your attention, the absorber and the stripper columns in this unit, they'd likely just be subcontracted to packing manufacturers to provide as a package. And that ships to the fabrication yard. So that in general is quite standard, but the absorber itself is split into, in this case, 3 towers, and they're side by side. So you have 2 towers of absorption packing, and then you have the water wash, acid wash, any other post-treatment on the flue gas that needs to happen in 3 separate units rather than stacking them. And the flue gas travels from the bottom of each one out to the top and down to an inlet at the bottom of the next tower. So this way, the full set of packing can be provided, but at a much lower visual impact than a single tower of the three stacked on top of each other. So the downside to doing that, and why we probably wouldn't do that on a full-scale plant normally, if we can avoid it, is the extra piping and the pressure drop, of course. But on a small unit, it's likely not to be too expensive to have the flue gas fans work a little bit harder, in exchange for keeping a low profile, especially for sites that have potential sensitivities around visual impact. So next slide, please. We'll now talk about the scale of the unit. So you may have noted from the description of the project that the original configuration for task 4 was written around the scale of a 100 ton per day unit. And that's where we started off in our assessment, and that is a facility, I mean, comparable to large pilot plants such as TCM, or indeed a full utilization unit as we see here on the left at Tata Chemicals. So that's a 120 ton per day unit. Clearly that's a sizable chemical plant in its own right. It would be challenging to move between facilities, as well as require a sizable footprint. So we've got an image here from Google Maps, and just outlining it's about 3,500 meters footprint. So as a result, the scope of the task was broadened to consider also if there are benefits at considering a smaller scale unit as the reference case instead. So, and the minimum for that was set following discussion with packing suppliers. That limit is about 0.4 meters diameter for the stripper column for an amine unit. And that's driven by getting representative packing performance. Of course, this is in a traditional static tower configuration. So the rest of the unit is then sized around the stripper column, and the scale ends up being round about 9 tons per day if you're processing energy from waste flue gas, and a little bit less if it's a CCGT flue gas, unless you make some changes and make the absorber slightly wider diameter to see more flue gas flow. So as a result, the minimum end of the scale looks something more akin to the NCCC plant in the States, and that's shown in the image on the right. And you can see that unit, the fabrication there, it really lends itself directly to construction in modules, and indeed shipping to site as a containerized, self-contained delivery that turns up, and all you have to do is erect it. So this facility may actually be mobile then, and that opens up options beyond the first test, because of course if you build the thing, you'd really like it to go on for a little while after the first use. And that would be things like moving a unit onto an R&D test plan where you look at advanced operating techniques, or things like just move on to another test site. So then there's the middle ground between these two, where you seek to both have a somewhat mobile unit but process a larger scale of CO2. That then leads us on into a discussion about the cost of the unit. So next slide, please. As mentioned earlier, we appraised the capex for the reference unit, and we looked at it at kind of 3 sizes. So we've got the minimum at the top of the 0.4 meter diameter unit through to the 100 ton per day, and we chose 20 ton per day as a reasonable kind of compromise between the two. So these costs have been calculated in pounds on a 2021 basis, ignoring any effects of current affairs. So the methodology used for working these out, it's consistent with a AEC class 5 estimate. So we've scaled from some previous work that we've done, and therefore it comes with associated uncertainty band. So for reference, at the bottom is a published EPC cost estimate for Tata Chemicals. So note the cost difference between the three sizes that we considered for the pre-deployment verification of the PDVU. You could, for the same investment as the full 100 ton a day unit, you could deploy multiple of the smaller units and gather data from multiple sites simultaneously. And the reality is, if we're talking about de-risking and we have multiple projects going on at the same time, then chances are we want to be able to de-risk multiple projects at the same time. And it follows that we probably want more than one unit. So next slide, please. Then we got on to looking at the schedule, and this has, so taking a month for some development and integration studies, following into a streamlined feed through to EPC schedule. The overall duration presented here represents the shortest duration we may expect to be able to design and procure individual equipment items and design the connection and fabricate the connection for the flue gas on site and so on, without needing to really rely on early procurement of long lead items such as the pack columns and the heat exchangers. And it's not a short period of time, given we want an extended test run once this thing is running. So next slide, please. That leads us on to next steps for the concept of this unit. So step one, we would like to have a discussion today with the people on this call and then wider as well, and gather feedback on the unit and we'll have some questions on afterwards. So after that, it would move on to identifying willing host sites and starting to talk or encouraging sites to talk about kind of the permitting of this facility. And really then a follow-on study. And I just want to be clear that the scope of our study is to outline the concept here and to provide this reference case. Although this is our proposal for what may be a reasonable test facility for carbon capture. Okay, so then I just want to move on actually and introduce the discussion questions. And this gets us on to, the first one being a case of, for those of you who are representing operating sites and looking to deploy carbon capture, is the scale that is suggested here for a de-risking concept, is that consistent with your plans? Are you looking at a larger scale or smaller scale? How do the timescales presented and the schedule presented, do those support the deployment of carbon capture for your sites? Do you, what are your thoughts on that? And then, we'd just welcome an open discussion on any interest in such a verification unit, developing that further, because really I think if you're exploring this idea, kind of now's probably the time to have these discussions with BEIS. And that is it for my content. Just want to open up to the first question. I think if John, you could moderate, that'd be great. Thanks.
Well, Karis also has some kind of specific questions that we were going to raise through a Zoom poll, just to get kind of ideas of, you know, sort of some just hands in the air kind of thing on a number of questions related to what Clem's just discussed. So these are really targeted at people on the call who are, you know, actual sort of industrial site operators who may be considering deploying carbon capture, just to sort of canvass views and get an indication of, you know, how the industry can, you know, would apply a sort of de-risking unit, or what kind of de-risking process you'd need to go through for deployment of full commercial scale carbon capture on your site. So Karis, I don't know if you can throw the first question up.
So I've just shared, first of all, just the results from the last one, just so we've got an overview of the numbers on the call, where people are from the call, just for anybody who's interested before I do the next question.
Thank you, Gary. Yeah, so good broad spread. So that's it, much appreciated. Thank you.
So I'll just launch the next one now. This is the first question.
So this question is really relating to, you know, the size and scale of your site, to put the you know, put the answers to the subsequent questions into context. So presumably, Karis, you'll see when sort of a representative number of people have answered that question, and we can go on to the next one, I guess.
Yes, we've had about 43% that have submitted. So shall I share them quickly so everybody can have a quick?
Yes, please. Yeah, because so if we're sort of just looking at, not everybody will be you know, be able to respond to that one.
So is that coming through for you without any issues?
Yep, got that. Brilliant. Thank you. Yep.
Okay, and I will launch the next question then.
So this is really fundamentally is the kind of long-term pilot plant concept that we're proposing, something that is relevant to de-risking deployment for a full-scale plant for your application. As Clem sort of discussed in his presentation, you know, it's really about the, you know, demonstrating the long-term solvent performance in specific applications for, you know, the immediate application that's being considered.
So we slowed down and stopped at about 35% there. So I'll just share those results for you.
Okay, that's very evenly balanced then. It's an interesting result, thank you.
And then the third question.
This is kind of a slightly different way of asking the same question, really about if you would be deploying or looking to run a long-term pilot plant, what sort of scale would it need to be to support the investment decision that would ultimately lead to deployment of a full commercial scale plant?
So we've still got a couple of answers coming in, I think. We've definitely slowed down now though. So I think I'll share there because we've stayed static for a few seconds there. And there's your results for the third question.
Okay, great. Yeah, that's some interesting feedback. Thank you very much.
And the final question, I'll launch that for you now.
And again, so this is referring specifically to the 9 ton per day kind of scale, 6 to 9 ton per day scale that we're proposing in the configuration that Clem's presented. The question is whether that specifically would support an investment decision for your full scale deployment.
Okay, so we've seemed to have slowed down at that point. So I'll share the next set of answers, or results, I should say.
Okay, great. Thank you very much.
You're very welcome.
There's a fairly balanced response to that as well. So that's interesting. Thank you very much. Okay, so appreciating that we are starting to come up against the time limit that we've allocated, or the time that we've allocated for today's call, are there any specific questions or observations or comments or responses in response to the notes or thoughts on the screen, or in response to Clim's presentation? Feel free to put something in the chat, and then okay, so Helen, thanks for your comment. Question about how this this unit and this proposal fits into the next gen study. It's not kind of directly informing the review of the next generation technologies. Kind of a supplementary part of the study. I think, Nick, do you want to comment or respond any further on that?
So I guess when we designed the study, we were keen to understand if we have future next gen looking to pilot at site. We wanted to get a feel for what would be the type of cost of such a unit to reference it against, and so that was one of the primary objectives. But then when we started looking at what might be the role of such a unit, it became apparent that there is this kind of gap in the long-term testing and for it to help sites reach that investment decision, given what we've seen on some of the earlier carbon capture projects at larger scale. So it's kind of it's naturally evolved.
Okay, great, thanks. Yeah, and that probably there's a link with that, with another comment and about any tentative schedule or plan for the next steps. And I guess, Nick, that's also kind of in your hands as much as ours.
So we don't have any separate funding to go out and buy a set of these units. We naturally know quite a few vendors are thinking about what type of offer they make to potential customers that are looking to deploy the technology. There is or my colleague will comment onto it, there is a second call for innovation projects. So if there was quite a strong desire from a set of clients to have a verification unit, there is at least a funding call available. I'll leave John to chat a bit more about that funding call, but there was no direct plans to have a separate program to fund these units as of yet.
Great, thanks. Yeah, Mark Summerfield, yeah, note your comment about these questions to a large extent are relevant to a financing audience as much as the others on the call. I guess it depends on the funding model for all the pilot plant and the full scale deployment. But yeah, we take note your comment, and happy to seek or receive sort of comments or thoughts from anybody, any stakeholder from relevant parts of the industry. Julian, your question on whether the slides videos circulated, yes, we'll be putting the recording and the slides on the UK CCSRC webpage for this project. And there's a couple of other comments. Lawrence, your question on kind of ethical aspects. I think there in the final report there is a sort of a quantitative as well as qualitative sort of commentary on the comment on the technologies. I think, I'm not sure if your comment relates to kind of next gen carbon capture generally and carbon capture more generally, or specifically at a differentiator between the different technologies. But yeah, there are bits of research going on within BEIS on the public perception of carbon capture and how it fits into the overall kind of transition to net zero, which not necessarily directly part of the scope of this project to assess relative performance, but yeah, a significant issue nonetheless. And regarding publishing of the plant study, yes, the concept, as far as it goes, is within the scope of this study will be one of the reports that's published as an output from this project, and that concept will be kind of available and publicly to form the basis for potentially proposals, as Nick says, for developing it for specific sites. So in view of time, and I guess people are sort of got other things to do and moving on to your next call as we do these days, we'll wrap things up there. I think, John, before we sort of do the full close, John Gordon, do you want to do you have a couple of slides on funding calls and
as we're running late for time, I can talk people through it. I think first of all, I'll introduce myself. My name is John Gordon. I am one of the program managers at BEIS, working on CCUS Innovation 2. I'll just talk to you about the innovation program for the next funding call 2, and we had call 1 earlier on in July last year. And we're now looking to progress with call 2. So we're looking to publish that information in May. It will broadly form the similar structure as we had with call 1. We have lot 1, which is mid-stage TRL projects, which there should be funding up to about £1 million for those projects and grant funding. We'll then also have lot 2, which will look at late-stage TRL projects. That's up to £5 million in funding. And we're also going to have lot 3 as well. So lot 3 is a bit different from what we had in call 1. It's new. We're looking to fund feasibility studies. Coming off the back of this study, really, for that. So we've got £50,000 is what we're looking at. We've mentioned this in the call 1 guidance, and we're looking to ring fence about £500,000 of that. So potentially up to 10 feasibility studies will be available in funding as well within call 2. We have around about £6.5 million available for call 2. So it is slightly, we'll say slightly less. It's half of what we had available in call 1. The contact details to get in touch with us is industry.innovation@beis.gov.uk. As the call guidance is published in May, as soon as it is published, we're able to answer any questions with any participants. So we'll be publishing more information around about April time about how you can register interest for that, and that'll be on gov.uk. If you're happy with for just contacting you using the details you've left in this chat, then please let us know. We can put you on a mailing list as well. But that's it from me.
Great, thanks very much, John. Yeah, so David, actually, if you scroll on to the next slide, I think that that email address is on there. So thanks, John. Also, the email address for any written comments or the representations, kind of in relation specifically to this study, the nextgen.ccus@aecom.com email address. And as I say, the interim reports that are being published this week and the recording and slides from today will all be on the UK CCSRC webpage that hopefully you've all visited anyway to be able to register for today's call. So apologies for running a little bit over time, but I think it was very useful to get the input and contributions from all the participants. Also, so thank you to the presenters today, and particularly the technology providers for producing and sending us the videos. And again, all of the technology providers' videos will be available on the UK CCSRC website, including those that unfortunately we weren't able to get for today's call, but there are, we're assured, other videos following on that will be going onto the webpage. So that's really everything we had to say today. Thanks again for your participation. Apologies for overrunning. Thanks for your input. Some very useful feedback from us, and I hope attendees have found it useful and informative. So with that, I'll say thanks again, and enjoy the rest of your day, and cheerio. Thanks.